Log on, tune in, find out. Another good idea from Cambridge.
And he's going to talk about the design of networked experiments.
So, thank you. Okay, so good morning. Thank you very much for inviting me. I'd like to say first of all that this work is some joint work with Steve Gilmore, who most of you will know, and John Shorman, who I'm fairly confident that nobody will know, except Steve Gilmore. Oh, yes, a couple of you. All right. So this goes on to demonstrate that it's a small world, which leads nicely into my talk. I always feel I should start my talk, now I've seen Ken's talk, with pointing out where London is. But let's just say it's a long way from Wagga Wagga, and you can work the rest out yourself. Okay, so I'm hoping to talk about something which is sort of a fairly general talk. It's the last talk in the session. I don't want to put a lot of algebra or sort of difficult equations for you to follow. And I'm going to be talking mostly about social networks and designing for social networks, and then tell you how we can maybe use some of that methodology to encompass a much broader class of designs which we're maybe familiar with. Okay, so when we design experiments, probably everyone here to a certain extent assumes that the subjects are independent, and that's pretty much what we always do. Okay, so particularly if we apply a treatment to one subject, we generally assume that the treatment does not affect any other subjects. Okay, but in this work we're going to investigate how the relationship between these structures affects how we might design the experiments on these structures. Okay, so very broadly, I'm going to consider a graph which is a collection of nodes n and edges e. Okay, so the nodes are going to represent some subjects on which we're going to apply some treatment, and we're going to have our normal little n subjects, which is going to be the size of the number of nodes. Okay, so our nodes are subjects, and the edges represent some relationship between the subjects. Okay, and I'm going to be quite broad about what that relationship is. So we're going to allow the relationship between our subjects to be specified by an adjacency matrix A, where Aij is 1 if I and j are related, and 0 if not. So if I and j are related, Aij is 1, and by convention you can't be related to yourself. Okay, so Aii is 0. So this matrix just sums up relationships. Right, so we're going to assume that our links are non-directional to start with, such that if I'm related to you, you're related to me, so that our matrix A is symmetrical. So here's a very, very simple network of 4 things. Okay, and we see here that, I was going to get the pointer out, but it's easier. 1 is connected to 2. Okay, so A12 is 1, and A21 is also 1. Okay, 1's not connected to 4, say, so A14 is 0, and A41 is also 0. And of course there's zeros down the diagonal. Okay, so this is a fairly standard way of representing productivity. Okay, so here's an example of a problem which we might be interested in. Okay, so the nodes might be subjects in a marketing experiment. Okay, so the links may be a social relationship, such as being friends on Facebook. Okay, I'm sure the vast majority of the young ones at the back will be on Facebook, and the vast majorities of the ones at the front will be wondering what a computer is. No, proud of it? Who is on Facebook out of interest? Yeah. Nobody, a few of you, excellent. Okay, you can add me later. Okay, so the treatments might be different advertising campaigns, such as Buy Coke or Buy Pepsi. I just point out that Queen Mary doesn't endorse either of these soft drinks, but these are used for the purposes of example. Okay, so the responses may be something like the amount of a product bought by a subject, or how much the subject likes the product. I'm not going to specify particularly here. Okay, so the concept is that if a subject's exposed to this marketing, okay, they might tell their friend may see the marketing. Okay, particularly a social network where you click on like and your friends will say, oh, Ben likes Pepsi. or Ben likes Coke, or whatever it happens to be. Okay, so by applying a treatment to a subject, it may also get applied in some sense to the friends of that subject. Okay, so we're assuming that if there is a relationship between two individuals, then the response from the first subject is dependent on the treatment applied to the second subject. Okay, you may think, okay, well that's stupid, I don't care about Coke, Pepsi or Facebook, and probably I agree with you. But here's a less trivial example. Okay, so we might have, the nodes might be subjects in a public health campaign, and the links might be something like two interventions, one of which might be, well, make sure you eat your 5 fruit and vegetables a day, and one might be, don't eat hamburgers, they kill you, or whatever it happens to be. Okay, so the response could be the change in fruits and vegetables eaten after the experiment, or it could be some, measure of heartbeat, or whatever it happens to be. Okay, so for example, a parent might receive some information on public health and pass it on to their child. Okay, my mother tells me never to smoke. She smokes 20 a day, but she's read the literature, she just doesn't want to do it for herself. Okay, so whether or not the subject sees the behaviour, it might bring a response about in their friends' behaviours, and their friends might be family, they might be friends on Facebook, they might be people they live with, whatever we want to define the relationship to be. Okay, so this might be something fairly useful. So I'll take you back to statistics 1, or statistics 101 if you're American and add 100 to everything. We've just got a simple model here. Our response Y is some mean plus the treatment effects toward J. So J is the treatment we applied to subject I, plus some error term, epsilon I, which is independently and identically normal. Okay? And just for uniqueness, we're going to fix tor m to be 0. Okay? So no problems there. So we're generally going to assume we want to measure the difference between some treatment effects. For example, here we might want to measure tor1 minus tor2. Okay? So in general, if we have a large enough experiment, we might want to measure something like the average, the variance in the average difference between treatment effects, okay, which works out to be that quantity. I'm not sure I said that quite right. So we've got the difference in treatment effects, the estimate, and the average variance thereof. Okay, and this is actually a optimality for estimating the difference in the treatment effects. Okay, for two treatments, okay, so we're getting 2 treatments. Anybody that's done a GCSE science test can tell you that a fair test involves giving half of your things treatment A and half of your things treatment B. Okay, so we all know that. So my idea is that if we apply a treatment L to a subject, there's going to be a network effect of gamma L to all neighbours of that subject. Okay? So, for example, if I apply treatment A to subject 1, you'll get an effect of gamma A on subject 2, as well as whatever treatment 2 has. Okay? So treatments will propagate down any link just once. They're not going to go down to second neighbours, but for this model, they're just going to go down the links to the neighbours and have an effect of gamma of the treatment. Okay?
Those effects are equally strong.
Sorry?
And those effects are equally strong, meaning one have impact. I understand there's impact to the other.
Yep.
Could be some stronger, some weaker.
Yeah, so gamma 1 might be bigger than gamma 2, say. But for the moment, if you're connected, the effect is the same. Okay? Or the, yeah. That is an extension we can look at. Okay, so is that clear? So we're going to introduce the linear network effect model, which says that our response is, as before, it's some mean plus the subject effect tor J for giving treatment J to subject I, plus an effect gamma L for all nodes which are connected to that node. Okay, so I get an effect from whatever treatment's applied to me, plus the sum of the network effects of the treatments applied to all my friends. Okay, so it's a fairly reasonable, simply formulation. So it's no longer clear from this that the balanced designs are A-optimal for estimating the difference in treatment effects. Okay, so before we said we'll give everyone half and half, now it's a bit less clear. So let's see if it is really the case. He says, knowing that the answer is clearly not going to be the case, otherwise he wouldn't have brought it up. So here's a random network, okay? This network has no significance whatsoever except that it's something that I can use to demonstrate. We can, by exhaustive search, look at the say optimal criteria for all possible treatment assignments. And here I'm assuming we've just got 2 treatments. If you notice, we have 10 nodes, and they're fairly sparsely connected. There's not many friendship nodes. So these might be, I don't know, computer scientists or something who don't. Funny, isn't it, that computer scientists invented social networks? But anyway, and this turns out to be the optimal design, okay? So this is the optimal allocation of treatment so that we can estimate the subject effects, okay? And of course you can swap the 1s with the 2s, there's nothing special about them, they're just coding. So what do we notice? Well, it's difficult to spot a pattern, first of all, but if you count the numbers that are given treatment 1, there's 1, 2, 3, 4 of them, and 1, 2, 3, 4, 5, 6 are given treatment 2. So if we want to estimate the effects of these 2 campaigns, this Coke, Pepsi, this Eat 5 food a day, whatever it happens to be, we no longer have a balanced design. Okay? Now the A optimal criteria is actually 0.418. It turns out, because you have 10 subjects and 2 treatments, that if you had no network effect and you were just doing an experiment on these, then you could get a variance of 0.4. Okay? So we're not actually far above that, but we can't quite obtain that 0.4 here because the network gets in the way. So this is the same network, and I'm just summarising what I said here. So this is the optimal design here. So we've got 1, 1, 2, 2 going around this way for estimating the difference in the subject effects. So, and we can also, of course, estimate the, estimate the difference in the network effects. Okay, so we might actually be interested to know, well, how good is our viral marketing? Okay, if I put Coke on Facebook, will people tell their friends about it, or does social health messages go down the line? Okay, and we get a completely different optimal design for estimating the network effects. Okay, we could come up with some kind of combined criteria to combine the 2, of course, but it's not obvious what scale that should be on, unfortunately. So it's possible to do, and we've done this by exhaustive search, so it's not incredibly computationally demanding for this particular example. And here's another network. So this network is more sparse, so this is obviously going to be statisticians who are friendlier and talk to everybody. But again, there's nothing remarkable about this. You find the design, and this time it does turn out to be balanced. Okay, so we have 5 1s and 5 2s. And that is the design, and it has optimality criteria of 0.406, again just slightly over 0.4.
The result depends on the degree of note.
Glad you mentioned it, I'll come on to that. So yes it does, but in a very non-obvious way, as far as I can tell so far. So let's say we have a network effect in our model, but we forget to include it. Okay, so this network effect exists, but we neglect the fact that our subjects are connected in some way. Okay, so what would we do? Well, we get 10 people in, and we give half of them treatment A and half of them treatment B. And being good statisticians, we'd randomise it. Okay, so because the nodes aren't special, if there's no network effect, it doesn't matter which we give it, treatment A or treatment B to. So if there's no network effect, then all permutations of the design are equivalent. I've just said that. Okay, but for our model, our nodes are special because they have connections. So if there is a network effect, even if we have a sample of 10 and 2 of the subjects happen to know each other beforehand, then our assumptions are broken down. Okay, so in a real social network experiment, if you're picking people from all over the world and doing the experiment remotely, then the network effect might not exist. But if we're going and doing a focus group in a university, say, and I say, Rosemary, what do you think of this new policy? And the head of department says, I don't like the policy, then Rosemary might say, well, I don't like the policy either because she wants to keep her job. Or she might say, oh, I like the policy because she wants to be contrary. I mean, I don't know. Okay? So this we're going to see if this network effect is important. Okay, so here's the second example I showed you, the slightly more connected network. And this red, which doesn't show up on this projector at all. So the second, the figures on the outside are just a random balanced design. Okay, so I've given 1, 1, 1, 1, 1 to the top, and 2, 2, 2, 2, 2 to the bottom. So I've just simulated what would happen if I didn't know there was a network here. Okay, so our optimal criteria we found was 0.406, but for our arbitrary design, we get a optimal criteria of 0.430. Okay, so our efficiency is only 94%, caused by neglecting the network effect. Okay, so I might have just chosen a random network to demonstrate this approach works. Okay, so what I did was I took 20 random networks, and for the first time in my life I did some box and whisker plots. No, that's not true. But we have 20, so each of these on the x-axis represents one random network, okay? And these are for a particular likelihood of things being connected, but the same principle applies for other parameterizations. Okay, and here on the y-axis we have the efficiency. Okay, so you will see that for each network the median efficiency is somewhere around 0.7. There's quite a big interquartile range. If you happen to choose a balanced design which is very bad, you can get less than 10% efficiency. Okay, so you can, if there is a network effect and you fail to include it and just are unlucky in choosing your balanced design, you get 10%. Of course, you might be lucky and you get 100% here. Okay, if you note here, network 17, I think, you can't get to 100% with a balanced design. So this network here is an example of one where the optimal design is not balanced. Okay, so there are real problems if we have this network effect and we fail to include it. Okay. So as well as causing high variance, it turns out that the bias, so this is the difference between our full model and our model without network effects and our model with network effects. So this is the bias in our estimators, is non-zero in general. Okay, and for our two examples, we can work it out. So just to skip over this quickly because I'm running out of time, but this beta is our two network effects, sorry, our two subject effects and our two network effects. And we, if we misspecify a model which has a network effect and we pretend it doesn't, then this is the way we can work out the bias based on the true value of those parameters. Okay, so as we expect, we misestimate the network effects by themselves. So, we've not got a network effect, so we're going to totally underestimate it by the true value. But our value of our subject effect, the bias in our subject effect, depends very strongly through these two numbers here on the network effects. Okay, so the bias can be significant, as well as the variance being, the efficiency being wrong. Okay, so if we have a network effect and we leave it out, it can be very bad indeed. So your question was, well, surely the design is, it depends on the degree. The design depends on the degree. Is that sort of paraphrase? So I thought, well, I'll look at that. I'll see how the properties of the network affect the design. So what would be really nice if somebody gave me a network and without going through an exhaustive search, I could just say, well, obviously you need to pick this design. Okay. So I learned about spectral graph theory. Spectral graph theory, the spectrum of the graph is the set of eigenvalues of the adjacency matrix A. Okay, so people just refer to the spectrum of the graph. We can look at the degree matrix, and that is defined as a diagonal matrix, and on each diagonal you have the connectivity of the subject. So if node 1 has 7 friends, then the 1, 1 element will be 7. Okay, and you can form the Laplacian spectrum by taking the degree matrix and subtracting the adjacency matrix and taking the eigenvalues of that. That becomes the Laplacian spectrum. Okay, well, why have I told you all that? These spectra are ways of summarising the macroscopic properties of the graph, if you like. Okay, so, okay, thank you. So, for example, the second smallest eigenvalue of the Placium matrix is the algebraic connectivity of the network. Okay, so if we're looking for some measure of connectivity, okay, so you might say, well, if we've got a very connected network, we need a different design from if we don't have a very connected network, then we can look at the second smallest eigenvalue. Or we can look at other eigenvalues which tell us different things. We can look at the degree matrix. So I thought, well, there's bound to be a clear link. There's bound to be a very clear link between these properties and the optimal design. But this is the kind of pattern we get. So on the bottom we have the algebraic connectivity, and here we have the value of the optimal design. Okay, and there is no clear pattern I can see. Okay, so it seems like this connectivity at least does not clearly determine what the value of the optimal design is. So it's no help in finding the optimal design for me. I also picked a random arbitrary balanced design and said, well, what's the average variance for that design? And as the connectivity of the graph goes up, the algebraic connectivity, the average variance just doesn't change very much. I mean, you might say there's a small upward trend, but it's certainly no help in finding the design. Okay, so my conclusions from this, well, probably even if you know the macroscopic properties of the graph, okay, it doesn't really help you in finding a design. So there's no clear link. And here's a sort of counterexample, if you like. Here are two networks, okay, and they happen to have the same spectrum. Okay, so these have, in many senses, the same properties, these graphs, but you can look at them and say, well, they're actually totally different. Okay, this one has an optimal design we can find, and this one is not estimable. Okay, we can't find all the subject and network effects if we try and design for this network. Okay, and you can find bigger examples where even the Laplacian spectrum are the same, the degree distribution is the same. It's just not the macroscopic properties that determine the design. Okay, we're getting some clues on what microscopic properties cause it, but unfortunately I haven't got time to go into that now. So I'm just going to finish with how long? 5 minutes, right? I'm just going to finish with two examples to show how we can broaden this into a much wider class of designs, and it may be something that's useful in your field. Sorry. Okay, so let's assume we're going to go to see Southampton this afternoon, and all the fields there are very neatly laid out in squares or rectangles. Now I happen to know that not all fields in the world are rectangular. So can we do a field experiment on a strange shaped field? Well, let's say we've got a field layout here. We've got plot 1, 2, 3, 4, whatever. So, you know, we might have another field taking up this room. We might have a tree or something here. So we don't really have a field which is, you know, we've got a field with a hole in it, essentially. And I'm going to assume that if you plant something in field 1, it's going to have an effect on field 2 and field 4. And we're also going to have any diagonal effects as well. So if you plant something in field 9, it may have an effect on field 5 or field 4. Okay, so we assume everything touches its neighbours. I can do it as a network if you like. So this is what it would look like in the standard way I've been presenting it so far. You probably can't see the optimal design there because it's too small. But this turns out to be the optimal design using that methodology. Okay, and it takes a couple of seconds. So if you can specify the connectivity structure of any field or any experiment that you can couch in this way, then you can very readily come up with an optimal design. It's interesting, the optimal value function value is 0.4055. If there was no restriction, then I had 15 plots, so I might be able to get 0.4. Okay, so I can actually do fairly well with this design, even for a fairly strange shaped field. Another example, let's look at crossover trials. Okay, so normally in crossover trials you assume that everyone's going to turn up, and you just will recruit on the basis that everyone's going to be there all the time. Let's assume that we're performing a crossover trial. We have 4 subjects, A, B, C, D, 4 periods, 3 treatments, and each treatment has a washout period of 1. So if you give a drug to somebody at time 1, it's still in their system at time 2. Okay, so on the recruitment stage, you tell participant B that he's got to turn up on the 2nd of September, and he says, oh, I'm going to a wedding, I can't possibly make it. And you've already spent £10,000 recruiting him. What do you do? Okay, do you go out and get another one, or do you say, well, let's redesign the trial for a planned dropout? Okay, so this is what the network would look like in my terminology. So we have a crossover trial, and here now we have unidirectional links. Okay, so these numbers now represent subject time combinations. So this is treatment 1 at time 1, subject 1 at time 1, subject A at time 1, and this is subject B at time 1. And 2 is related to 1, but it's not related forward to 3. Okay, so we can now modify our adjacency matrix A such that it's unidirectional. Okay, so the theory doesn't change at all, it's just the way that you do the search is now slightly different. Okay, and again we can find the A optimal value for measuring our treatment effects, and this is what it turns out to be. Okay, so there's nothing sort of remarkable in that itself, but the fact that we can take this social networks work and we can use it on a much wider class of experiments, and we can do it very quickly, for me is quite exciting. Okay, and once again we can get fairly close to 0.4 even though a subject has dropped out. Okay, although we have to be quite careful here, should I be comparing with 16 treatments or 15 treatments, but I'll leave that up to somebody who's more expert in crossover trials. So to conclude, I presented a new method which takes into account very simple relationships between subjects when we construct a design. I'd be very happy to hear if other people are doing this, but I don't think I've come across anything in this way in the literature. It's very useful for social networks, but there's a very wide class of experiments where this methodology will work, and I presented a couple here. For me, it's interesting to challenge our standard assumption about independence of our units. People do that, but they tend to do it in a very sort of fixed way. So you have a left effect or a right effect, and this allows a much more general relationship structure. I've hinted at this, but our matrix A can represent anything you want it to be. So it could be the strength of a relationship, it could be one-way relationships, for example. So this is quite flexible. And I've assumed there's one relationship, so we could easily extend it. We could introduce another friendship relationship to introduce a blocking effect, or a second friendship relationship, or a geographical effect. And all that would do was just increase the search space a little bit. We've considered unstructured treatments in here, but we've done some work already with other treatment structures, factorial treatments, and we also get some very interesting results in there. For more complicated experiments, we need to do some more work on actually the design algorithm, because as you get more treatments and more subjects, it gets quite large. But there are ways we can reduce the state space and make this possible. And actually this work is very interesting as well. It's mathematically very, very nice. Partly because this hasn't really been done, I don't really know of any experimental data to sort of try it on. So if you know of anyone doing anything on this, please do let me know, that would be great. And that's all. Thank you very much.
Okay, we have time for one quick question.
You have demonstrated that balanced designs are not good in the example of 10 nodes.
Mm-hmm.
What about balanced design in stronger sense? In the sense that with edges take into account?
But it's not clear to me how you do that.
Let's say I have a situation where I can divide the 10 nodes into 2 groups,
Mm-hmm.
and each have 5 nodes. And now I obtain one graph by removing all the edges in group 1. Then I obtain another graph by removing all edges in group 2. Let's say the 2 graphs in some way close, isomorphic.
Yeah.
And would that be auto design?
It helps you find the design, certainly. So as a way of finding the design, and one of the things we've looked at is what they call automorphisms. Okay, so it's ways of sort of eliminating symmetries in the graph. So yeah, you certainly could prove that certain designs do have a certain graphs do have a balanced design. But for a general method, I think it requires quite a lot of
I
thought.
know it may not be possible to do it, but if that's true, if I can obtain two groups that are not balanced, but approximately balanced in that stronger sense,
Yeah.
the design probably will be very good.
Maybe. I don't know, I'm sorry.
Okay, let's thank Ben again.